8.2. This word is pronounced, in this particular context, arithmetic. It is not arithmetic.
It is.
This is an adjective. It is used to describe the word sequence. It is also used to describe the word series. When it is an adjective, we say arithmetic, not arithmetic. So it is arithmetic, and we're going to all practice it. Ready? Again, it's arithmetic. Ready? 1, 2, 3. Arithmetic. Very good. And you guys are so funny. Anyway, I'm going to first give you a couple examples of arithmetic sequences. Okay, here are 2 examples. You can write these down if you wish. You don't need to, or you can write a few of the terms down. But you should be able to recognize the pattern. And then once you recognize the pattern, we'll talk about that and then explicitly state what an arithmetic sequence is. So in the first sequence, what is the pattern? Plus 3. So we're going to add 3 every time, and we get the next term. All right, what is the pattern for the second sequence? Minus 10. What would be another way to say minus 10? Subtract 10. That would be another way. Could you give me yet another way?
Negative 10.
What about the negative 10? What about the negative 10?
Plus negative 10.
Plus negative 10. Here's why I wanted to say that. Okay? While you were all correct, the reason I want to focus on addition is because that is what the definition of an arithmetic sequence is. Okay? If for some reason you couldn't figure out that this was plus 3, if I just went 7 minus 4, that would give me the common difference. Or 80 minus 90, that would give me the common difference. That's all that. So when the sequence goes up or down by the same amount when adding, again, this was plus 3, this was plus negative 10. That is known as an arithmetic sequence. Here we go. So there's going to be on this page, do not take a picture of this screen yet. I'm going to fill the rest of this box out. And once I get to the end of the box, if you wish to take a picture, you can. There's going to be a lot of formulas, definitions, terms that we need to know. And this is the beginning of it. When we come up with an arithmetic sequence, remember that the braces indicate the entire sequence. Right? This is the first term, a sub 1. When we add that amount, whatever that amount is, to each term, that is known as the common difference, known as D. So to get to the second term, I take the first term and add D to the first term. And this becomes the second term. Then I would add another D to this term to get the next term, which would mean I would have 2D. And then it just keeps going on like that. Now, notice the so each time you add another D to get the next term. And the term number, so the first term, obviously, you don't add the common difference. The second term, you only add 1 common difference. So to get the third term, you add 2 common differences. And so it's always 1 less. And so just so you are clear, here's a sub 1, this is a sub 2, this is a sub 3, this is a sub 4. So the number of common differences that you add to the first term is always 1 less than the term number. Okay? And the reason I'm going through that is to show you where the formula that you're going to need to know comes from. So we'll get to that in a second. To be clear, if we were looking at it in a recursive way, we just always add the common difference to the previous term. And that's how we come up with the sequence. There are going to be some cases, in the first 2 examples I gave you, we were able to see the common difference really easily. It's plus 3, plus negative 10. Sometimes you'll have fractions and decimals and you won't be able to tell what the common difference is. So if you needed to figure out what it was and you knew you had an arithmetic sequence, you can just take the preceding term and subtract the previous term. And just subtract those 2 and you'll get the common difference. All right, so let me flash back over here. What this is saying, okay? If you couldn't see what the common difference was, just subtract the 2 terms and you'd be in good shape. Now, formula for the nth term of a sequence, of an arithmetic sequence, and this is where I was talking about the number of common differences being 1 less than the term number. That's why you see this n minus 1. You're going to need to know this formula. The nth term equals the first term plus n minus 1 common differences. And again, you see that pattern going on here. One less number of common differences added to the first term will give us the whatever term we're looking for. And then the last formula is the recursive formula. And the recursive formula will pretty much always look the same, will always come in the same form, and you have to have all parts. In order to come up with the recursive formula, you need the first term, you need whatever term before the term we're looking for, and then we can find it from there. So here's what that looks like. Now the box is complete. If you want to take a picture of the screen, you can. But here's how the recursive formula is defined. You must state what the first term is. You have to say a sub 1 equals whatever. Then, as we learned before about recursive formulas, the trick is I take whatever term I'm looking for, and it equals the term before it plus the common difference. And then you have to state this for n greater than or equal to 2. And the reason why we have to state that is because if for some reason n was not greater than or equal to 2, we run the risk of this being a sub 0, and we don't know what a sub 0 is. Okay? We always start with sequences with a sub 1. So when you get to writing your recursive formula for an arithmetic sequence, you must have 1, 2, 3 things. And that will happen. And we'll go through some examples so you can see what I mean. Are there any questions so far? All right, let's put it into play. So here's a couple examples. All right, so to Joaquin's question earlier, one of the things you're going to have to do is determine whether or not we have an arithmetic sequence. And if it's not, what is it? Well, in this case, we're just going to say that it's not arithmetic. So either it is arithmetic or it's not arithmetic. That's it. Okay. In this particular example, if it is arithmetic, we also have to state what the common difference is. So let's do that. Is A arithmetic?
Yes.
Why?
Negative 10.
Okay. So plus negative 10. So what we would say is yes, this is arithmetic. And the common difference is negative 10.
Could you just write yes?
It doesn't really ask for that. I'm not going to get hung up about it. Okay. How about B? Is B arithmetic? No. So it goes up by adding, but it doesn't add the same amount, right? So what's the difference here? 4, then it's 5, then 6. So it is adding, it's just not the same amount. So then we would say this is not arithmetic. And we move on.
Is there a name for it?
But is it
No, not for this one. There is one other one that we'll look at for 8.3, but otherwise no. Okay. That's how some of your homework will start off. It'll be pretty simple. Right? And we just get progressively more difficult, starting with this problem. Okay? So we did some problems like this in 8.1 on day 1. You know, we wrote the first so many terms of a sequence. In this case, it just happens to be arithmetic. Okay? They give us the first term, and they tell us the common differences for. Then what I want to also spend time on is talking about the recursive formula. So my first term, right, is negative 5. Go ahead, and I want you to find the next 4 terms, which would give me the first 5 terms. So go ahead and do that now real quick. So what is it? What do I have to do in order to find the next term? Just add 4. So when I add 4, what do I get? Negative 1. Okay, so there's the second term. How do I find the third term? Add 4 again. What do I get? 3. Then what? Then, there you go. First 5 terms. So this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. How many had that? Raise your hand. Okay. Pretty simple, right? There it is, typed up nice and pretty. Okay. Let's find the recursive formula. Again, you need 3 things. So first off, you have to state what a sub 1 is. What is it? -5. Okay. Now, the next part of the formula will pretty much always be the same with one exception. The common difference will change per problem. So I'll have, to find the nth term, I have to take the term before it, n minus 1, a sub n minus 1, and add to it the common difference. Well, what is the common difference? 4. And then the only thing I have to say, so the third thing is I have to say for n greater than or equal to 2. And you must always include all three of these things. Okay, so you got to have this, this, and this. You have all three of those things, you've got your recursive formula for an arithmetic sequence, and you're good to go. Okay? Yep, that's all you have to do. Okay?
Why did you write greater than?
What did I write? What?
Greater than or equal to 2?
Because that always has to be there. If you look in the purple box from the previous slide, it has to be there. It's always going to be here because this can't ever be 0.
Is that ever different? Number 2?
No, this will always be n greater than or equal to. This will be different based off of the common difference. Yes.
Is that same thing? Just a
Yes,
different
this will be
form?
the same. This will be the same always.
Okay.
The only thing that changes is the common difference. Correct. But this n greater than or equal to 2 will always be there.
Well, you have
All
to
right?
write that out for.
Yes, you have to write that.
2.
What's that?
The number 2.
Yes, the number 2 will always be the same. Because again, what we're guarding against is this becoming 0 somehow. And if we didn't make this restriction, there was potential for n minus 1 to equal 0 or negative, which doesn't make sense, so we don't want to have that. All right. Now here's, I had it all written out. There's the actual formula, and there we filled in for D, same thing. Okay? All right. More problems. This is example 4 from your book. All right. We're asked to find the 9th term of the arithmetic sequence in which a sub 1 equals -4. So the first term is -4. The 22nd term is 164. Now, what don't we know? Yeah, I don't know the difference. I don't know how much is being added each time to get from -4 to 164, let alone to get even to the second term. We don't know that. All right? So we need to find the common difference. We need to find D. And we have enough information to find D. So this is where that other formula is going to come into play. And we're going to use that. So here's the other formula. This is the formula for any term, the nth term, if you will, of an arithmetic sequence. Fortunately, because we know the first term, we know this. In this case, we're going to use the 22nd term for a sub n, which means n will be 22. So I'm going to so I've got 1, 2, 3, 4 things in this equation. If I know 3 of them, I can find the 4th one. Okay? So in this case, I have the 22nd term. So n is 22. Now I can substitute those values in, right? A sub 22 is 164, and the first term is -4. So now I have everything. So go ahead and find D. You've got everything you need except D, so find that, please. Okay. What did you get? What does D equal? D equals 8. Okay. So we can simplify this down. Add 4 to both sides. That's 168 divided by 21, so D equals 8. Now, I'm not going to ask you to, find the second term, third term, fourth term, all the way up to the 9th term. That would be a lot of work, and we don't need to do that. What we can do now is, since we know, so if we use this formula again, I still know the first term. Now I'm going to be looking for the 9th term. So all I need to do is plug 9 in for n, and now that I know that D is 8, we can find that 9th term pretty easily. Okay, so here's what it would look like on my next screen. Now, I've got one more step because the book likes to simplify this first. I'm not a fan of that. I think at this point, let's just go with a sub 9. Now I can plug 9 in for n. And I can simplify this, and that will give me a sub 9. Okay. So this is negative 4 plus, what's this over here? 64. So a sub 9, not g, equals 60. Okay. That's how I would do this problem. Now, I'm going to show you the way the book has it written out because they like to simplify this formula. You're going to get the same answer. I don't care which way you do it. To me, it would make the most sense to go ahead and just plug the 9 in right away and figure it out. But it's up to you. So let me show you how the book has it. They basically distribute the 8 and simplify the right-hand side first. Okay. And so this is my formula, and then they plug the 9 in. Which, whatever, you get the same answer. It doesn't matter. You don't have to put it in like this. Okay. You could put the 9 in right here and simplify to get to the 60 like I showed you. Either way is fine. Whatever you think is easiest, whatever you think suits you best, go for it. Okay? Any questions on that? All right. Let's look at another one. This particular question is asking for the number of terms. So the last problem I had to find the common difference first, then I could find the specific term. This one is asking for how many terms there are. Okay. So we start with 7, 3, negative 1, and then all of a sudden we have these 3 dots that mean there's a bunch of numbers in there, but we don't know what they are. So what we're looking for in this problem is n. We're trying to find n. So, since this is the first term, and this is the last term, if I can figure out which term number this is, then I'll know how many terms there are. All right, so we start our normal formula. What is the common difference here? Negative 4. So that's why it's really important that we think about adding all the time. The common difference is actually negative 4. We don't know n. We know the first term. And we know the last term. And that would be the nth term. That'll tell us how many terms there are. So it's just a matter of plugging all that in. And I have, again, I have 4 things missing, but I have 3 that I can plug in. I have the last term, the nth term, which will tell me how many terms there are. I have the first term, and I have the common difference. So go ahead and solve that and figure out what n is. You probably distributed first. That would be my guess. That's what I've done. All right, so this is negative 4n plus 4. Combine like terms, that's 11. Subtract the 11. Okay. And then I flip sides. So, bless you. So right over here, it would have been negative 124 equals negative 4n, which I could solve to. You know, we like to have stuff positive. So what does n equal then? 31. Which means there are 31 terms. Okay? So that's my sort of last step. There are 31 terms. Find the number of terms. N equals 31. Just show that you understand that the relationship between n and the number of terms. Okay? That's how you would find the number of terms. Now, some of these problems can get a little more complicated and they don't quite give us enough information. And I'm going to show you 2 ways to do this next problem. First I'm going to show you the book's way. Then I'm going to show you my way, and I think you're going to like my way better. Okay? So, any questions so far? Okay. So here we have 2 terms of a sequence. We have the 15th term, which is 49, and the 27th term, which is 85. They tell us that it's arithmetic. They want the 500th term. Okay. So we got to see how much information we have. Do we have the first term?
Yeah.
No, we don't have the first term. Do we have the nth term, the 500th term? No, that's actually what we're looking for. All right. Do I have n? Do we know how many terms are in the sequence? No. Do we know the common difference? No. Doesn't feel like we know much. So here's how we're going to set this up. Okay? And what this says is we're going to use this formula twice, and we're going to have to set up a system of equations. Now, let me show you what it looks like. Then I'm going to show you that there's a better way to find the common difference than what the book shows. But I like to show both so you can have both to choose from. It's up to you. Right? So I could use this as my 15th term, make n 15 and a sub 15 49, which would mean I would have this term filled in and I would have the n filled in. I wouldn't know the first term. I still wouldn't know the common difference. Same thing here. I can use this 27 for n. 85 becomes my 27th term, and n becomes 27. I still don't know the first term or the common difference. So here's where my system would come from. So over here I have the 49th term, or the 15th term, excuse me, which is 49. I plug 15 in for n. And I would simplify that. So this is 49 equals a sub 1 plus 14d. Then I have this other term. 85 is the 27th term, so 27 goes in for n. And then this equation simplifies like this. A sub 1 plus 26d. Now what I can do is solve that system. Probably the easiest thing to do is eliminate the a sub 1 first and solve for the common difference. And here's what I mean by that. I'll just copy this over here. And if I just change all the signs, then the a sub 1's drop out. Okay. So I have negative 36 equals negative 12d. Did I do, was my math right? Okay, so what does d equal? 3. So the common difference is 3. Now, once I find d, I can go back up to this equation. I've got my space over here, so I might as well use it to find the first term. And that's 26 times 3. So I've got 85 equals 81 plus, what's 26 times 3? 78. So what is a sub 1? 7. Okay. Now I have everything I need. Okay, this is one way to do it. This is one way to do it by solving a system. But there's another way to find the common difference. You're still going to have to set up one of these equations to find the first term. Actually, no, I take that back. Yeah, we're still going to need to solve to find the first term. But there's an easier way to find the common difference, another way. I won't say it's easier. I'm going to say it's another way. Let me show you. I'm going to do this over here on the side. Does anybody else think they know a way to find the common difference without doing a system? From using the first two terms, any ideas? What's the difference between 49 and 85? How far apart are they? They're 36. So this would be, so in other words, 85 minus 49, that equals 36. Okay? What is the difference between 15 and 27? 12. So if I was looking at that, it would be 27 minus 15, which is 12. What do you suspect I do with those things? That's another way to find the common difference. Now, you're still going to have to set up one of these two equations here. It's just a matter of solving for the first term, because I need the first term in order to find the 500th term. So this might save you a little time finding the common difference. You'll set one of these up to find a sub 1. So, for example, if I mean, if this was my problem, if this is one I chose to use, I'd plug 3 in here, and this is 42. 49 minus 42 is 7. Okay? Or I could have just as easily used this one like I did and plug 3 in. I guess what I'm telling you is this is another option rather than necessarily using a very strict system of equations. I'm leaving it up to you though, okay? Now, here's all the steps from the book. Here's the system. They went ahead and plugged it in and solved it just like I showed you, but I wrote it all out. Now, all of this is just to get us to a place where we can find the 500th term. Because when we look at this formula, the 500th term is, n is going to be 500. So I'm going to plug 500 in here. Now I know that the first term is 7. I know the common difference is 3. So in order to find that next term, we just have to plug all that in. And so here's where that is. So the 500th term is going to be the first term, which is 7 now. We figured that out. Plus, 500 minus 1 times the common difference, which is 3. So now we just got to figure out what that is. 1504. That is correct. Okay, so that is the 500th term. You could do 499 times 3, but I mean, this is 1500 minus 3. That might be easier to use distributive property, actually. 1500 minus 3, 1497 plus 7. Okay. So yeah, there's a little more work to do when they don't give you the first term or the common difference. When they just give you 2 terms, there's a little more work to do. So be careful when you get to problems like that, all right? Any questions so far? This is the end of sequences. Now we're going to shift to series here in a second, okay? All right, here's what it is all typed out. We went through that. Great. All right, let's talk about series. Evaluate a finite arithmetic series. Now, you don't have to write what I'm going to show you here down. This whole slide is a proof of where the formula for the nth partial sum comes from. Don't write it down. You don't need to take a picture. Just pay attention. Sometimes I like showing you guys proofs because it's a little higher level stuff. And I think sometimes to know where things come from is important. So we're using this example. We have this finite arithmetic sequence, 1, 4, 7, 10, 13. 5 numbers. It's going to be really simple. All right. You could add them up and come up with the sum. But I'm going to show you where the formula comes from so you can kind of get the idea. You will not need to know where this formula is derived from. You will not need to demonstrate the proof of it or anything like that. I just like to show it to you. The series or the nth partial sum, it has to be finite for arithmetic. If it was infinite, it would either be positive infinity or negative infinity. We'll get to one's infinite series for another type of sequence that I'll teach you in 8.3 where you can actually have a sum for an infinite series, but you can't for arithmetic. All right, anyway. So, of course, the first partial sum is just the first term. The second partial sum is the first 2 terms added together, etc. The third partial sum is the first 3. Okay, and so this is where each partial sum comes from. The second partial sum 5, third partial sum 12, fourth partial sum 22. So I'm just adding up as I go. Fifth partial sum 35. Now, so that's the answer, right? The series, the fifth partial sum is 35. So here's where the formula kind of comes from as an example. So what we're going to do is we're going to put the terms in opposite orders, ascending and descending, and then we're going to add them together. So this is the fifth partial sum, 1 plus 4 plus 7 plus 10 plus 13. Now we're going to flip the order around. What do they all add up to? 14. They all add up to 14. So if I added 2 of the fifth partial sums together, I would get 14 plus 14 plus 14 plus 14 plus 14, which is 70. Okay. Which is 5 times 14. And so that ends up giving me 70 divided by 2, which is 35. So let me write that out just so you can see. So this is 2 fifth partial sums equals 70 divided by 2, and that's where my 35 is, which we already knew the answer, okay? Now, why this is important is to kind of show you the formula. And I'm going to put this on the next screen for you in a second, all right? Because this is the basis for that formula. So on the next screen, I'm going to put the formula up. So on the next screen, you should take a picture of it, all right? This is the formula for any nth partial sum of an arithmetic sequence. And this is the one that we just did. The difference between what's written here and what we did is this. It would be like this. N times a plus 1 plus a sub n all over 2. That's the difference. Our way looks like this. Now, whichever way you do it is up to you. You'll get the same answer. Okay. So the first term plus the last term, and that's where all those 14s came from. The first term plus the last term, that gave us 14, times the number of terms, all divided by 2. And the divided by 2 comes in, remember when we added the two equations together, we got 2s sub 5. In this case, s sub n, right? So this formula you need to know. Whether it's in this form or this form, I don't care. But if it asks you for the nth partial sum of an arithmetic sequence, okay, the finite arithmetic series, this is the formula you're going to use. You just need the first term and the last term, number of terms, and then you're good to go. Okay. So when you're finding the nth partial sum, it's actually there's less work usually than for the sequence. All right, we have one example to look at, and then we'll be done with 8.2. Any questions on the formula? All right. Find the sum of the first 50 terms of the sequence. If we think about our formula, here's our formula. I need 3 things instead of 4. I only need 3. I need the common difference. Sorry. I don't even need the common difference. I don't know what I'm talking about. I need the number of terms. So how many terms, what's n going to be in this problem? 50. N is going to be 50. Do I know the first term?
2.
Yeah. Do I know the 50th term?
No.
No. I only know the 5th term. I need the 50th term. If I had the 50th term, I'd basically be done. Because I have, this is what I have so far. I have s sub n equals 50 over 2 times 2 plus a sub 50. Right? I don't have the 50th term. That's the thing I'm missing. That's the thing I'm missing. And that's this. We just need the 50th term because we know everything else. So I need to find the 50th term. Well, we have a formula to do that. Okay, so we have to find the formula for a sub n, or in this case, a sub 50 first. That looks like this. So what is the common difference? We do actually need the common difference. 2. We need the common difference because we're going to find the 50th term. I plug. That's 2. All right, I know the first term. So here, I just need to find the 50th term. This is 2 plus 50 minus 1 times 2. So what is the 50th term?
100.
All right, so this is 49 times 2, which is 98, plus 2, which is 100. So the 50th term is 100. So then I just go back to the formula that I just had. So I've got 50 terms. I know the first term, it's 2. I now know the last term, it's 100. So this is, here's how I would do this. This is 25 times 2, which is what? 50. 25 times 100 is 2,500. So what's 2,500 plus 50? 2,550. What this means is that the first 50 terms of this sequence, when we add them up, will equal 2,550. Okay. Again, what you would see in the video is them simplifying this because a sub n just equals 2n. But to me, there's no sense in doing that. You can just go ahead and do it that way. Okay?
So
That is now it.
that is so much.